Hi, everyone. Welcome back to the second part of chapter 6. In the first part, we talked about chemical calculations, especially introduced the concept of mole, which is a very important quantity describing the amount of a substance. And also, more importantly, the concept of mole can relate to the actual number of something, which we're using 6.02 times 10 to the 23rd. But also, mole is related to mass using molar mass. So today, this half, we're going to keep talking about chemical calculations, but now we're going to apply the calculations and the concept of moles into chemical reactions. So first, let's take a look at what is a chemical reaction, and more importantly, how do we represent chemical reactions? Okay, we use chemical equations to represent chemical reactions. Like I show here, this is an example of a chemical equation. You can see that substances are separated by an arrow, okay, an arrow from left to right. And the substances that are on the left side of the arrow, we call those reactants. It means they're participating in the reaction. And substances on the right side of the arrow, we call them products. And those are what are produced from the reaction or after the reaction. And of course, we use plus signs to separate different reactants or different products. If you have multiple reactants or multiple products, you use plus signs to separate them. So this is the basic language of representing a chemical reaction, and we call that chemical equation. Now, if you really want to read that language of chemical equation, you can read like this. For example, this is an equation showing the reactions of hydrogen and oxygen to produce water. So you can read it like hydrogen react with oxygen to produce water or produces water. So the arrow actually pronounces or reads as produces, and the plus reads as add. So basically you're separating different reactants. So you can actually convert that chemical language into just basic language of reading out the chemical equations. Now, one thing very important about writing or representing chemical equation or using chemical equation is the fact every chemical reaction has to satisfy the law of conservation of mass. Okay, we may have mentioned that in earlier chapters. If you remember, we said in chapter 1, atoms are the smallest building blocks for substances, and also the basics of chemistry, the basic entities of chemistry. And also during chemical processes, during chemical changes, chemical reactions, atoms themselves actually don't change. They simply rearrange, right? If you remember that we talked about in chapter 1, you would now have a better idea that if the atoms simply rearrange before and after reaction, what happened is before and after the reaction, you should have the same number of atoms for each element because the atoms don't change; they just rearrange, right? Like a Lego piece, you just break them apart and make a new one, but use the same pieces. So before and after the reaction, you should have the same number of atoms of each element involved in the reaction. So another word is on either side of the arrow, you should have the same number of atoms of each element. And that is called the law of conservation of mass. You have to satisfy that. If an equation that does satisfy the law of conservation of mass, having the same number of atoms of each element on both sides, we call the equation a balanced chemical equation. And a balanced chemical equation is a valid chemical equation. That means all chemical equations have to be balanced. They have to be balanced. So if you take a look at the reaction below here, an example reaction below here, the one we have just shown, hydrogen react with oxygen to produce water, you will find out the reaction itself actually doesn't satisfy the law of conservation of mass. On the left side, you have 2 hydrogen atoms. On the right, you do have 2 hydrogen atoms. But on the left, you have 2 oxygen atoms. On the right, 1 water only have 1 oxygen atom. So in that sense, the reaction is not balanced. So in order to balance a chemical equation so that they satisfy the law of conservation of mass, we have to do something. We have to add numbers. Okay, we have to add numbers in front of the substance. Okay, for example, in this case, I can add a number 2 in front of hydrogen, add a number 2 in front of water. Okay, if I add these two numbers, 2 and 2, you will find out now on the left side of the arrow, I have 2 hydrogen. Okay, each hydrogen has 2 hydrogen atoms, so we have 4 hydrogen atoms. On the right, I have 4 hydrogen atoms because each water has 2. I have 2 water, so 4 hydrogen atoms. Also on the left, I have 2 oxygen atoms, and on the right, I have 2 water. Each water has 1 oxygen, so 2 water have 2 oxygen. So in that case, after I put 2 and 2 in front of hydrogen and water, I found out the reaction now has the same number of atoms of each element on both sides of the arrow. So this reaction is now balanced. Okay, it is now a balanced equation. So that means I'm adding some number, and the numbers I actually just added in front of the substances are called the coefficients. Okay, the coefficients. Coefficients tell people the relative numbers of molecules or of reactions of products. Basically, you can change the number of the molecules involved in the reaction. Okay, it changes the amount, the numbers of them, but you don't change the identity. Okay, you didn't change the identity because you're adding how many substances are involved. You're not changing the identity of the substances. Now, if a coefficient is 1, you don't need to show that in an equation. Just leave that as it is. You don't have to put a 1 in front of it. Now, since we're talking about adding number in front of each substances, we also have numbers as subscripts. And we know these subscripts, we studied many times before writing chemical formulas, we know the substances are determined by what? Determined by the nature of the substances. Hydrogen is H2, oxygen is O2, water is H2O. So that means the subscripts are the numbers of atoms in the molecule that is determined by the nature of the molecule, depending on by the molecule itself. That is not something you cannot change. Okay, subscript is something you cannot change, but you can always play with the coefficient. That means the number in front of the molecule, because you can change the quantity of the molecules involved in a reaction so that you can balance them. Okay, and finally, if you use coefficient, multiply the subscripts, you can get the total number of atoms involved in the reaction. For example, 2 times 2 here, I get 4 hydrogen involved. 2 times 2, I get 4 hydrogen involved. 1 times 2, I get 2 oxygen. 2 times 1, I get 2 oxygen produced. So you see that I use coefficient, multiply the subscript, I get the total number of atoms for each atom. I can calculate the total number of atoms for each element. Okay, for each element. But again, before I move on, one more word, that is, you can always change this coefficient in order to balance an equation, in order to satisfy the equation, the law of conservation of mass, but you can never ever change the subscript. Okay, change the subscript. Concept check. Okay, I'll leave it up to you. It's a very simple question. As a practice for you, which one of the following is true regarding balanced chemical equations? I'll leave it up to you. The key is available. Okay, next. Okay, very important is, since we know reactions must be balanced, reactions represented by chemical equations must satisfy the law of conservation of mass. So if I give you an equation, or if you write an equation based on the information given, how do we balance a chemical equation? How do we start with adding the coefficient? Which coefficient should I add first, or which next? So what are the general rules? Okay, normally balancing chemical equations are very straightforward, but there are some rules will make the balancing process a little more easier than if you don't follow. Okay, but again, I think if you play with the coefficient, eventually you can balance them. Okay, so these are the simple rules. Like I said, may make your balancing process a little smoother than without the rules. Okay, the first is, take a look at the equation. Pick one element to balance first. Okay, pick one atom to balance first. And then the element you pick, okay, the element you pick, better to be the one that appeared only once on either side of the arrow. Okay, if you use that, if the element you pick to balance, if it only appears on either side of the arrow once, balancing will be a lot easier. Then after that, do the same thing, pick another element, and then until everything is balanced. Okay, so for example, this equation, you can see that the equation is given. Of course, apparently it's not balanced because there's 2 chlorine here, there are 3 chlorine here. So 2 chlorine, 3 chlorine is not balanced. So in order to balance it, of course, we need to change the coefficient, right? And we can even start with chlorine because we're talking about chlorine, and chlorine only appeared once in the equation. So let's start with chlorine. One is 2, another one is 3. How do we make it balanced? I change the coefficient here to 3, change the coefficient here to 2. Okay, as you can see here, after I change the coefficient, write it down again. Okay, after I change the coefficient 2, 3, and 2, you will find out I got the smallest whole number, 6, right? 3 times 2, 2 times 3, 6. So that means either side, I have 6 chlorines. Okay, chlorine is balanced. Okay, after I balance chlorine, I know 2 in front of here. Change the number of iron to 2. So I need to put a 2 in front of this iron as well. Okay, because I need to balance iron as well. Okay, iron 2. Now, after I put iron 2 here, I change the number of iodine to 4. 2 times 2, which is 4. So I change this one to 2 as well. So after that, I think our equation is balanced. Okay, 2 iron, 2 iron. Okay, 2 iron, 2 iron. 4 iodine, 4 iodine. 6 chlorine, and 6 chlorine. See, if you pick one element, again, the element you pick usually, we pick the element that appears as once on either side of the arrow. We'll make it easier. And then you pick another one. And then, again, make sure you double check. Do you have the same number of atoms on either side of the arrow? Right? Okay, this is another example. Okay, let's try it together. Like I said, I pick an element that only appears once on either side of the arrow. So I pick calcium. Calcium is balanced. You can see 1 calcium and 1 calcium. So I'm good. But then I move on to oxygen because oxygen only appears once. Here on the right side, I have 2 oxygen, but on the left, I have 1. So I put a 2 in front of calcium oxide. Okay, after I put 2 in front of calcium oxide, the oxygen is balanced, but the calcium on the right is no longer balanced. So I need to put another 2 in front of that calcium to make sure calcium remains balanced. Okay, now after I balance calcium and oxygen, okay, I know they're balanced. The only thing that's not balanced is the carbon. So I count how many carbon on the right side of the arrow. 2 times 2, there are 4 carbons here. Okay, and also 1 carbon here. So I have total of 5 carbons on the right. So all I need is balance with a number 5 in front of carbon. So after that, you can again double check. 2 calcium, 2 calcium, 2 oxygen, 2 oxygen, 5 carbon, 4 plus 1, 5 carbon. So if that's the case, the equation is balanced. Okay, equation is balanced. Next, the equation itself is not given. Ask you to write the equation and then ask you to balance the equation. So here I'm gonna write the equation with you. Okay, I think I can write this way. Okay, I can write this way. They asks, what is the correct balance the equation for the process of heating, sodium bicarbonate. If you guys remember, sodium bicarbonate is NaCO3, okay, CO3, and heating the sodium bicarbonate to produce, once you hear that to produce, you know that you can insert an arrow, right? So let's go ahead, insert an arrow. Okay, of course, on paper is much easier. Okay, insert an arrow. And then to produce what? Sodium carbonate. Okay, you have to write the formula. Sodium carbonate is Na2CO3 and carbon dioxide, and then what? Water. Okay, water. And finally, let me change the numbers to subscripts. Okay, change the number subscript. So now we got the equation. Okay, the equation is written. Okay, based on the information given, heating sodium bicarbonate to produce sodium carbonate and carbon dioxide and water. I got the equation. Okay, all I need to do now is to balance it. Okay, they balanced it. If you notice that on the right side, I have 2 sodium. So first, I need to put a 2 in front of the sodium bicarbonate to balance the sodium. And then what's amazing about this reaction, you will notice that after I put the 2 in front of sodium bicarbonate, hydrogen and oxygen are actually balanced at the same time. If you notice that after I put a 2 in front of here, I got 2 hydrogen. Okay, I got 2 hydrogen on the right. I got 2 hydrogen from water as well. After I put a 2 in front of sodium bicarbonate, I have 6 oxygen. You count here on the right, there are 3 oxygen, 2 oxygen, and 1 oxygen. Total is 6 oxygen. So after I put a 2 in front of sodium bicarbonate, the reaction is actually already balanced. Okay, already balanced. Okay, so these 2 are examples for you or exercises for you to complete. Again, the equations of them are not given, so you need to, based on the statement, to write the equation first. And then after you write the equation, you go ahead and balance them. Okay, I think I provided the key in the note area. If not, again, feel free to ask me questions. I hope you do practice the simple topic of balancing chemical equations. Okay, now after we balance our chemical equation, okay, with not yet. Okay, there's something to consider. Okay, something extra consider of balancing chemical equation. That is, again, subscript cannot be changed. We emphasized this before, but something we did emphasize is when you balance the chemical equation, you will add the numbers. Okay, add the numbers. Make sure you always use the smallest set of a whole number. Okay, that means usually when you balance the equation, we don't use fractions, but we use the smallest set of a whole number. Okay, smallest set of whole number. What does it mean? You may still, what do you mean? Let's try this equation. You will see in general what that means, smallest set of a whole number. So this is the equation over here. You can see that there are 2 carbon on the left. So I put a 2 on the right, carbon on the right, and there's 6 hydrogen on the left. So I put a 3 on the right. So there's 6 hydrogen, right? That's easy part. But now let's count oxygen. Okay, on the right, there are 2 times 2, 4 oxygen, 3 times 1, 3 oxygen. So I have 7 oxygen on the right. Okay, if I have 7 oxygen on the right, I know in order to make 7 oxygen, I put a 3.5. Okay, 3.5 in front of oxygen in order to make a 7. Okay, now you see that in order to balance the equation, I have to put a 3.5, which is not a whole number, which is what? Which is a fraction. So in order to solve that problem, and remember, right now, my equation is actually balanced. It's only thing is the problem is the equation contains a fraction coefficient. So what I do here is basically multiply every single coefficient by 2, because I have a 0.5 fraction. In order to convert it to the smallest whole number, I can just multiply by 2. So multiply the 1 by 2, this one becomes 2. Multiplies 3.5 by 2, this one becomes 7. Multiply 2 by 2, this one becomes 4. Multiply 3 by 2, this one becomes 6. So 2, 7, 4, 6 are actually the balanced coefficient. Now you see that left side have 4 carbon, right side have 4 carbon. Left side have 12 hydrogen, right side have 12 hydrogen. Left side have 14 oxygen, right side have 8 plus 6, 14 oxygen. Okay, you can see that because of that fraction, and also because we need a small set of whole number, I multiply a number 2 to make the smallest set of whole number instead of using fractions. Okay, instead of using fractions. So that's what I means. Okay, next, small things. Sometimes when we balance the equation, after we balance the equation, we also can indicate the physical state of some substances in the chemical equation by using the first letter of the state in a parenthesis. For example, you can see that in first equation, the G stands for gas, and here S stands for solid, and G, of course, stands for gas. So you can indicate okay, indicate the state, physical state of these substances, of these reactants and products using the first letter of the state in the parentheses. Of course, L stands for liquid, okay, for liquid. So that's something to talk about before when we balance a chemical equation. Okay, after that, okay, like I said, I skipped one step. Now it's for real. After we balanced a chemical equation, okay, we have coefficients in front of each substance. We know the equation is balanced, and because the equation satisfies this law of conservation of mass. Now the question is, what these coefficients are used for? And of course, they're used for balance the equation, but what is the deep meaning of these coefficients? Okay, the coefficient, in fact, in the chemical equation tells us the relative amount of these substances in moles involved in the reaction. Okay, they're not just numbers balancing these equations. They're actually the amount of the substances in moles that are involved in the chemical equation. Okay, for example, the equation shown here, it means 4 moles of iron reacts with 3 moles of oxygen, produces 2 moles of iron trioxide. Okay, 4, 3, 2 are actually in moles. They are relating the amount of these substances in moles. Okay, that's the deep meaning of using these coefficients, because they're relating the substance in the unit of moles. And because of that, they're relating them in moles, I can create many conversion factors relating these substances, and they're all in moles. Okay, for example, I know 4 moles relate with 2 moles of iron oxide, or 2 moles of iron oxide react with 4 moles of iron, or 4 moles of iron relates 3 moles of oxygen, or 3 lights of oxygen relates 4 moles of iron. You can see that these are the conversion factors, and these numbers are related or from the coefficients. And I can create pairs of conversion factors using the quantity of these. And that also tells us the substances that are related or involved in a chemical equation are related in what? In moles. If I know the mole of one thing, I can calculate the mole of another using the coefficients because they're related. And the calculation shown here, the moles of A relate to the moles of B using coefficients. The calculation shown here, remember, we just do a lot of conversion factors. That is called the stoichiometry calculation. Okay, that's a very important calculation in chemistry, because if I know the mole of one substance, I can calculate the mole of another because they're related by their coefficients in moles. That is the beauty of stoichiometry. But there's one simple problem. That is, usually in a chemical equation or in the real lab setting, okay, research setting, the amount of the substances are not given or measured in moles. Okay, we don't have a equipment to measure mole, but we do have a balance in our lab, or you have a balance in your lab kit to measure what? Measure mass in grams. So that means if you want to relate the substances in moles, okay, moles of A and moles of B, if you want to relate them in moles, you have to convert what you can get, that is grams, to moles. And after you relate them in moles, you have to convert the mole of B back to what? To grams. So that means before and after the stoichiometry calculation, you have 2 more steps to go. That is, convert the grams of A to the moles of A. And after relate the moles of A and B, you have to convert the moles of B back to grams of B. Because remember, what we measure in real lab setting exercise is still in grams. Okay, in grams. So that means stoichiometry is relating by coefficient. But then before and after the stoichiometry, you need to convert back to grams and mole and grams. And this brings us to what we learned in previous part of this chapter. What relates gram and mole? Molar mass reacts to gram mole, because molar mass is grams per what? Per mole. So basically, before and after the stoichiometry calculation, you will use the molar mass of A and molar mass of B to convert grams to mole and mole back to grams. Okay, that is the whole sequence of chemistry calculations. Okay, here let's take an example. Okay, a real example. If 2.5 grams of sodium chloride, this is the formula of sodium chlorate, decomposes, the products are actually sodium chloride and oxygen gas. Okay, this is the lab actually we can do in our lab. Okay, if you are in face-to-face chemistry 101 class, we're actually doing this lab. Okay, and this is the equation. Of course, we balance the equation by adding a 2 in front of sodium chlorate, 2 in front of sodium chloride, and 3 in front of oxygen. So this equation now is balanced. And after balance, we know these three substances are related by 2, 2, and 3 moles. Okay, 2, 2, and 3 moles. Okay, that's the information. And then the question tells us how many how many grams of sodium chloride can be produced if you start with 2.5 grams of sodium chlorate. Okay, sodium chloride can be produced. Okay, this is what they need to do in grams, and from 2.5 grams of sodium chlorate. Okay, we know these two guys, sodium chlorate and sodium chloride, are related by what? By coefficient 2 and 2 moles. Okay, 2 and 2 moles. Okay, that is what we show here. Okay, 2 and 2 moles. 2 moles of sodium chlorate, 2 moles of sodium chloride. Okay, that's from the equation. But what we were given is not mole, is gram. So like I said, I need to convert first sodium chlorate. Okay, convert sodium chlorate, 2.5 grams, to mole of sodium chlorate first. Using the molar mass here of sodium chlorate. Okay, you can see that I put grams on the bottom because I want to cancel the grams to get what? To get the moles. Now, after I get moles, I can relate the moles of sodium chlorate to the moles of sodium chloride, 2 mole and 2 mole, because they're by the coefficient. Okay, again, the given unit is always at the bottom, so we can cancel. And then after I get the moles of sodium chloride, they need mass. So I need to convert the moles of sodium chloride to the grams of sodium chloride using the molar mass of sodium chloride, right? 58.4. So 3 steps. The first step is converting the mole of sodium, converting the grams of sodium chlorate to the mole of sodium chloride. Second step, mole to mole. And third step is convert the mole of sodium chloride to the grams of sodium chloride. Of course, I cancel the units. I do all the mass. 2.5 times 2 times 58.4 divided by 106.4 divided by 2. I got 1.4 grams of sodium chloride. Okay, 1.4 grams of sodium chloride. Okay, 1.4 grams of sodium chloride. Okay, 2 sig figs because I was given 2 sig figs over here. Okay, I put the logic below there. You can see that what conversion factor are we talking about? Now, sodium chloride is a product, and we calculated that from 2.5 grams sodium chloride, I can get 1.4 grams of sodium chloride of product. And that is called a yield. We can yield this much of sodium chloride product. And because the yield is coming from the calculation, from the stoichiometry calculation, we call that yield theoretical yield. Okay, very important, theoretical yield. In theory, 2.5 will yield 1.4. That's the maximum you can get because that's from calculation, from paper. Okay, that yield 1.4 grams of sodium chloride is called the theoretical yield. Okay, theoretical yield. Now, like I said, theoretical yield is from paper. In reality, if you do the reaction in the lab, you may not end up getting 1.4. The amount you get will always be the same or less than 1.4. So the actual amount you got, okay, you obtained from a lab, like you weighed in the end by the end of the day, is called the actual yield. That means how much sodium chloride you actually got on your hand. If you use actual yield divided by the theoretical yield multiplied by 100%, you get a ratio or percentage. We call that percent yield. Okay, we call that percent yield. So these three types of yield are very important regarding chemical reactions to evaluate how good the reaction is. Okay, higher yield means the reaction works great. Lower yield means the reaction is not so good. But the three types of yield, you have to know which one is which. Theoretical from calculation, actual from experiment. Percent is actual over theoretical multiplied by 100%. Okay, so for example, followed by the previous question, if you actually got one gram of sodium chloride, and our theoretical is 1.4, we know that. So if you use 1.0 grams of sodium chloride divided by 1.4 grams, multiply 100%, you got 71%. And that's called the percent yield of this reaction, which is a medium, slight over medium yield, not a great yield. Okay, so that's the overview of chemical calculations. Okay, very quick concept check before we can do a comprehensive practice together. Okay, this one asks you, what would be the percent yield for a chemical reaction where the theoretical yield is 5.6 and the actual yield is 4.5? Okay, 4.5. So we know we use what? 4.5 grams divided by 5.6 grams times 100%. Okay, times 100%. I think the answer will be around 80%. Okay, so I think it is B. Okay, 80%. Okay, answer is around 80%. It's a very straightforward calculation. Okay, next is a comprehensive practice. Okay, I put the key here, but I want to go over with you. And again, when you practice, I hope you to cover the key, do them again and again, so you get all the ideas about moles to grams, gram to moles, stoichiometry, and yield calculations. Everything, the whole logic flow. Okay, so here's the question. They ask, when 12.3 grams of hydrogen, this guy, react with nitrogen to produce ammonia, NH3. Okay, the reaction is balanced. You can see that I put the coefficient in different color, just show you it is balanced, but you need to always double check if the reaction is balanced or not. And then they tell you 55.8 grams of ammonia are obtained. What is the percent yield? Okay, we know percent yield is actual over theoretical. Okay, you didn't ask yourself, do we know both? The question tells us 55.8 of ammonia are obtained. Obtained means what? You actually got. So that means what? We know the actual yield of 55.8 grams. That's how much we got, obtained. So in order to know the percent yield, I need to calculate what? Theoretical yield. Theoretical yield came from what? Stoichiometry, right? Theoretical yield come from stoichiometry. Okay, theoretical yield coming from stoichiometry calculations. So let's take a look. How do we calculate ammonia? Remember, we were given 12.3 grams of hydrogen. So I need to look hydrogen and ammonia, how they're related. I'm given a hydrogen. I want ammonia. So I want to know how they're related. They're related by two numbers, 3 and 2. What? Moles. Okay, moles. But I'm given grams. So I need to convert grams of hydrogen to moles of hydrogen first. So first multiply 1 mole of hydrogen is 2 grams. That's the molar mass of hydrogen. And I put grams in the bottom to cancel the grams. I get the moles of hydrogen. Then 3 moles of hydrogen, I get 2 moles of ammonia. That's from the reaction. Okay, 3 moles of hydrogen, 2 moles of ammonia. I put moles of hydrogen in the bottom. I can cancel moles of hydrogen. And finally, I get the moles of ammonia. I need to convert moles of ammonia to what? 2 grams of ammonia. Using the molar mass of ammonia, NH3, 17 grams. Okay, so after those 3 steps, I got the theoretical yield of ammonia. Okay, one more time. Grams of hydrogen, multiply the molar mass of hydrogen, 1 mole over 2 grams, I get the moles of hydrogen. And then 3 moles of hydrogen relates to 2 moles of ammonia. So 3 moles of hydrogen, I get 2 moles of ammonia. I get the moles of ammonia. And then I need to convert the moles of ammonia to the grams of ammonia using the molar mass of ammonia, 17 grams. So after those 3 steps, okay, I cancel the units. I didn't cancel numbers. So you need to put all the numbers into prac tube exercise. So in your calculator, you need to put 12.3 times 2 times 17.0, divide by 3, divide by 2, divide by 1. Okay, the dividing ones, put a parenthesis over there. Okay, so you don't mess up the calculation. And then what you got the yield from stoichiometry calculation is called the theoretical yield. And then I use the actual yield divided by the theoretical yield, multiply 100%, I get the percent yield, 365, 80.1%. Okay, see, that's the basic overflow of stoichiometry calculation. Okay, the last question I want to leave up to you. Again, I have some hint or some clues down there. Okay, help you to get started. And it's a very similar question, okay, asking you to calculate the yield. Here, you don't even need to calculate percent yield, just ask you to calculate theoretical yield because they're asking the number of grams of CO2. Okay, I'm going to CO2. So I have some clue down there in the notes. I hope you'd use it and practice them again. Even the questions we have keys in my lecture notes, I hope you to use them well and practice them without the notes. Take a look at the note and practice again. If you have any doubt, questions, feel free to ask. Okay, that is all for chapter 6. I'll see you guys in chapter 7. Bye now.